Now we've written complex numbers in polar form using the complex exponential, we can now talk about complex numbers to various powers, and we can also find what are called nth roots, which generalize ideas like the square root and cube root and so on. Let's begin by looking at the number I to the I to see how to find powers of complex numbers. It's a very instructive example, and it's perhaps worth just thinking about what you think the answer might be before we actually work it out. To calculate it, what we need to do is to write I in polar form. So I has a modulus of 1 and an argument, principal argument of pi by 2. So therefore, I can raise it to the power I by using the usual rule for powers, so I have e to the minus pi by 2. So it comes out to be a real number. But actually, that's not all, because I can actually have I written as the set of numbers, e to the I pi by 2, plus 2n pi I, where n is an integer. So it's a family of numbers if you write it like that. All of these equate to I, but when we raise this to a power, we suddenly have a sequence of real numbers. So this illustrates rather nicely why having all arguments, a set of arguments, is important when we consider powers of complex numbers. So although I written out like this all evaluates to the same number I, when I raise it to the power I, it becomes a sequence of real numbers. Let's now consider complex numbers to fractional powers. So for example, I want to consider things like z to the half, z to the third, and so on. In order to do this a bit more carefully, what I'm going to do is look for solutions to equations like this. If I want to solve an equation like this for z, I'm looking at w to the 1 over m. How do we go about finding these solutions? What we're going to do is write both sides in modulus argument form, and I'm just going to illustrate how to do this with an example. So let's try and find the cube root of 2 minus 2i. Now, rather than writing 2 minus 2i to the 1/3, I'm going to write this as find the solutions of the equation z cubed equals 2 minus 2i, solving a polynomial in z if you like. Then if I let z equal r e to the I theta, raising it to the power 3 gives me r cubed e to the 3i theta, and writing 2 minus 2i in modulus argument form, 2 minus 2i we get in modulus argument form just by considering where it is in the complex plane, 2 along, 2 down, making an angle pi by 4 with the positive real axis. And because it's below it, the argument is negative. So now I can equate the moduli and the arguments. So r is 8 to the 1/6, and theta is minus pi by 12 plus 2/3 n pi. As n varies over the set of integers, there are 3 distinct roots. Z is a set of points on a circle of radius 8 to the 1/6. So on a circle of radius 8 to the 1/6 is where all these solutions lie. So Z is a set of 3 points on this. The principal value is below the real axis with an argument of minus pi by 12. Add on 2 pi by 3 to that, and I end up with a number up here. So this is for n equals 1, 4, so on. Add on another factor of 2/3, and we get our third distinct root. So a cube root generally has 3 distinct roots lying on a circle with the radius determined by the modulus of what you're taking the root of. Let's say we want to take the number minus 1 to the power 1 over 6. What's that going to give me? Well, I'll go through the same procedure where I take z to the power 6 equals minus 1 and ask what are the set of z values that satisfy this equation. Again, we write down z in its modulus argument form because that's equal to minus 1, that's equal to e to the I pi, and so we can see that r is equal to 1 and theta equals pi by 6 plus 1/3 n pi I, giving me z. And these points, again, they all lie on a circle. In this case, it's the unit circle. We have 6 distinct points now, and they lie on the unit circle. The first one makes an angle pi by 6. The rest are spaced around the unit circle with an angle pi by 3 apart. So we can see that I and minus I are solutions.